For examples for vector-valued functions, example 1, r of t is the position vector of a particle in the plane at time t, where they give us r of t. So we can also write this as a vector in this form. So root 3 secant t, root 3 tangent t. And that's the form that I'm going to use the rest of this problem, just for my own ease. Find the velocity and acceleration vectors. So part A, the velocity vector has a function value of, we're just going to take the derivative of each part. So root 3 is a constant, and the derivative of secant t with respect to t is secant t tangent t. So we have root 3 secant t tangent t, and then the y component is root 3 secant squared t. If we take the acceleration vector valued function, that will end up being taking the derivatives of the velocity vector valued function. So we have, for the x component, root 3 times secant t tangent squared t plus root 3 secant cubed t. That comes from the product rule, because when we take the derivative of secant, we get secant tangent. So that's the first part. And then that's times the tangent that was already there. That's why we have a tangent squared. And then when we take the derivative of tangent, that's secant squared, and that's multiplied by the secant that was already there, and that's why we have secant cubed. For the y component, it's root 3 times 2. I'll put a 2 out in front. Maybe I'll erase it and write it a little bit neater. 2 root 3 secant t times with a chain rule component. So then the derivative of secant is secant tangent. And since we will then have secant appearing twice, we'll have secant squared t tangent t. So that ends up being the acceleration vector. Part B, the speed is the square root of each of the components. So root 3 secant t tangent t squared plus root 3 secant squared squared. So that ends up being the velocity. If we're, the speed, which is basically the absolute value of velocity. So when we end up doing this with 0 in there, we get the square root of 0 plus root 3 squared, which just ends up being square root of 3. Notice that means you have to know that secant of 0 is 1 and tangent of 0 is 0 in order to do that problem. Secant of 0 is 1. I can't remember if I said that, but secant of 0 is 1 and tangent of 0 is 0. Part C. In order to do part C, to find the angle between the velocity and acceleration vectors at the given value of t, since t is 0, that's actually going to make this problem pretty easy, but we have to know that the dot product is equal to the x components multiplied together and the y components multiplied together, or it's also equal to the magnitude of u times the magnitude of v times the cosine of the angle between them. So if we want to find the angle between them, we can divide by the magnitude of each of u and v and then take the inverse cosine. So theta is equal to the inverse cosine of u dot v over the magnitude of u times the magnitude of v. So if we take a look at u dot v, in this case, u and v are the velocity and acceleration vectors, because that's what the question is asking for. So that basically means we need to do v of t dot a of t. And if we do that, we end up with, well, I'm not actually going to do that because that's a lot of writing, but I will do v dot a evaluated at 0. So if we have v of 0, that's root 3, 0. And if we have a of 0, that's 0 root 3. So if we dot those, we have root 3 times 0 plus 0 times root 3. So that's 0. So if we take a look at this, we're having the cosine inverse of 0 over whatever the magnitude is. It doesn't really matter. But that means we have the cosine inverse of 0, so theta, in this case, is 90 degrees, or pi over 2 radians. Problem 2. Position of a particle at any time t greater than or equal to 0 is given by x of t and y of t as given there. Find the magnitude of the velocity vector at t is 4. So v of t, I'll write that in component form. Actually, I'll write it with i's and j's just for fun. So we have 2ti plus 6/5 t squared j. So now if I want v of 4, I just substitute in 4. So I get 8i plus 96/5 j. So I can write that as 8 comma 96/5 in component form too. So I want to find the magnitude of this. So that's the square root of 8 squared plus 96/5 squared, which ends up being 20.8 or 104/5. Part B, find the distance, the total distance traveled by the particle from t equals 0 to t equals 4. So that's the integral from 0 to 4 of the square root of dx dt squared plus dy dt squared dt. So dx dt was 2t, dy dt was 6/5 t squared. And so I take that, I substitute it into an integral calculation either on Desmos or on my TI, and I end up with 4144 over 35, which is approximately 30.696 to 3 decimal places. Part C, if I want dy dx, I can do this in 2 different ways. I'll take dy dt over dx dt, which is 6/5 t squared over 2t, which is the same thing as 6/10 or 3/5 t. And then if I notice that in the original problem, x of t was equal to t squared minus 2, I can solve for t, and I get the square root of x plus 2. Now notice that technically t could be plus or minus the square root of x plus 2, but since in the original problem I was told that t is greater than or equal to 0, I'm only going to use the positive case of this. And that's important to actually understand that algebraically it could be plus or minus 2, but within the context of the problem, t must be positive or equal to 0. So that's why we're only taking the positive case. So I can make a substitution, and that ends up being 3/5 square root of x plus 2. The other way I could do this is I could have made substitutions at the beginning of the problem. So I'll show that really quick. Dy dx. If I notice that y of t is 2/5 t cubed, I could just make the substitution right here. So that's 2/5 times root x plus 2 cubed, which is 2/5 times x plus 2 to the 3/2. And if I just take dy dx of this, I get 2/5 times 3/2, which is 3/5, and then x plus 2 to the 1/2, and that actually gives me the exact same answer. as I had right here. So I could have done it using previous methods if I made a substitution early in the problem. Example 3. At time t equals 0, a particle is located at the point 1, 2. It travels and has an initial direction in a straight line. So that's important to note. Initial direction of travel in a straight line toward the point 5, 1, has speed 2 at 1, 2, and has constant acceleration 3I minus j. Find an equation for the position vector r of t of the particle at time t. So notice that a of t is 3I minus j, or 3, negative 1. If I write the velocity of this, so v of t, that's essentially integrating this. So I end up with 3ti minus tj plus some constant, and that constant has components. So that's something to keep in mind. The constant will have I and j components. Now, one thing that's important in this problem that you have to be aware of is if we are starting at 1, 2, and we are initially heading in the direction of 5, 1, that means that my initial speed or initial speed velocity, sorry, I should use proper terminology. My initial velocity is going in this direction, and it has magnitude 2. Okay, so my initial speed is 2, and the velocity has direction headed straight line toward 5, 1. So what that means is that the unit vector of my velocity, is going to be traveling at 4, negative 1, and I'm going to multiply that by 1 over root 17, because if I do 4 squared plus negative 1 squared, I get 17, and if I take the square root of that, that ends up giving me the magnitude, the magnitude of what 4 and negative 1 would do. So if I want to unitize that, I would divide that by root 17. Since it tells me that my initial speed is 2, that means that I'm going to want to multiply 4 over root 17, negative 1 over root 17 by 2. So that means that my constant in this case is 8 over root 17, negative 2 over root 17. So that's kind of an important thing. You have to understand that the slope of this, like if we're thinking in algebra 1 terms, the slope of this is negative 1/4. So that means that my vector has to be going in that direction. So the y component has to be negative 1, the x component has to be 4, and then we want to unitize it and then multiply it by 2 so that our speed can be exactly what the problem tells us the speed is at that point in time. The reason that works as c is because this occurs at t equals 0. So when v equals 0, this goes away, and we're just left with c. And we know that c is 8 over root 17i minus 2 over root 17j as a result of what we just calculated. Hopefully that makes sense. So that means that if I write v of t, now that I know what c is, I have 3t plus 8 over root 17i plus negative t minus 2 over root 17j. So now I know that. Now I'm going to finish the problem by writing r of t. So I'm going to anti-differentiate this. So I get 3/2 t squared plus 8 over root 17 t plus, or I'm sorry, I. There will be some constant component to this, plus negative t squared over 2 minus 2 over root 17 t j, and then plus some constant. And we actually know what this constant is, because when t equals 0, I know that I'm at the point 1 comma 2 because that's what the problem tells me in the first sentence. So since that's true, when t equals 0, notice that all of this will go away, all of that will go away, and so my c has to end up being I plus 2j. So therefore, my final answer, since c is equal to I plus 2j, um, r of t is equal to 3 halves t squared plus 8 over root 17t plus 1 I plus negative t squared over 2 minus 2 over root 17t plus 2j. And again, that's because I know that c is at 1 comma 2. Well, I shouldn't put 1 comma 2 in parentheses. I should put 1 comma 2 in component form if I'm going to write it like that. Example 4, the path of a particle for t is greater than or equal to 0. Notice that's important, is given by r of t equals that function. A, find the coordinates of each point on the path where the horizontal component of the velocity function is 0. So let's find the velocity function. That is, in component form, 1 minus 2 over t squared and 6t. The horizontal component is 1 minus 2 over t squared. We want that to equal 0. So that means 2 over t squared equals 1, which means t squared equals 2. So t equals square root of 2. Actually, algebraically, again, it's plus or minus the square root of 2. But since t must be greater than or equal to 0, we only look at the positive value for t. So since we want the point on the path, that means we're going to substitute root 2 into the original. And so we get the point is root 2 plus 2 over root 2, comma, 3 times root 2 squared. And that is root 2 plus 2 over root 2 is the same thing as root 2 plus root 2. So I get 2 square root of 2, and then the y part is 6. So the point on the path is 2 root 2, comma 6. Part B. We're going to find dy dx when t equals 1. Once again, the velocity is 1 minus 2 over t squared I plus 6t j. So if I'm looking at dy dx, I have 6t over 1 minus 2 over t squared. If I want, I can multiply the numerator and denominator by t squared. So I get 6t cubed over t squared minus 2. If I want to write it in a little bit simpler form, it's not necessary, but you could. When t equals 1, that means I have 6 over 1 minus 2, which is 6 over negative 1, or negative 6. So that is dy dx at t equals 1. Part C. If I want d squared y over dx squared, I will take the derivative of dy dx and then put that over dx dt. So dy dx is derivative with respect to t. I will take this one just because it's a little bit easier to look at, but you could definitely use the unsimplified form, and it's not a problem. You won't get in trouble. I'm just using the simplified form for my own ease. Its derivative of the top is 18t squared, and then you multiply it by the bottom, minus the derivative of the bottom, which is 2t times the top, so that's 6t cubed, all over the bottom squared, so that's t squared minus 2 squared. And then we have to divide that by dx dt. dx dt is 1 minus 2 over t squared. This can be simplified in many, many ways. A final simplification, I'm doing this skipping a lot of steps, but that's 6t to the fourth times t squared minus 3 all over t squared minus 2 cubed. It's really not necessary to do all that. You can actually get the answer without doing a whole lot. The problem said we need y equals 12. Now when y equals 12, that means 3t squared equals 12. So t squared equals 4, which means t equals plus or minus 2. But once again, we don't need the plus or minus because t has to be greater than or equal to 0. So that means t equals 2. So if I substitute t equals 2 in here, I end up getting 12.